We know that the rate of a reaction depends on the concentration of its reactants or on the pressure in case of gaseous reactants. Along with concentration or pressure, temperature also has a major effect on the rate of a reaction. It has been observed that generally rate of reaction increases with an increase in temperature. Also, it has been found that an increase of 10 degrees Celsius in temperature doubles the reaction rate. The dependence of the rate of a chemical reaction on temperature can be explained using the Arrhenius equation. The Arrhenius equation gives the relationship between the rate constant K of a reaction and the absolute temperature T. It is defined as K is equal to A multiplied by e to the power minus EA divided by RT, where K is the rate constant, A is the frequency factor, which is a constant specific to a particular reaction, EA is the activation energy, R is the gas constant, and T is the absolute temperature. To understand this better, let us consider the reaction between chlorine nitrite and nitric oxide. In this reaction, a chlorine atom is transferred from one molecule of chlorine nitrite to a molecule of nitric oxide. According to the collision theory, in order for the reaction to occur, the nitrogen atom in NO must collide with the chlorine atom in ClNO2 with sufficient energy and the correct orientation. Before chlorine nitrite and nitric oxide are converted into products, during which existing bonds break and new bonds are formed, they go through a highly unstable intermediate or transition state. If we plot the potential energy of the molecules versus the reaction coordinate, we get the curve shown here. The peak of the curve is the transition or the intermediate state, which is also known as activated complex. The energy required by the reactant molecules to reach this transition state is known as activation energy, EA. In other words, this is the minimum energy required to cause a reaction. Even though the overall delta G of the reaction may be negative, the reactant molecules still need to go through the transition state in order to react. It is important to note that according to the collision theory, only a small fraction of the collisions produce a reaction. These colliding molecules must collide with the proper orientation with sufficient energy, called threshold energy, which is the energy possessed by reacting species plus activation energy. Hence, not all molecules have enough activation energy to take part in a reaction. If we plot the fraction of molecules with the given kinetic energy, we get the Boltzmann-Maxwell distribution curve shown here. Only those fractions of molecules on the right-hand side of the activation energy take part in the reaction. As the temperature of the system increases, the peak of the curve moves to a higher energy value, and the curve broadens out to the right, such that there are a greater number of molecules with much higher energy. As the number of molecules with higher kinetic energy increases, the number of molecules that carry energy greater than the activation energy also increases. Thus, the rate of reaction increases with temperature. In the Arrhenius equation, the factor e to the power minus EA by RT corresponds to the fraction of molecules that have kinetic energy greater than EA. Taking natural logarithm on both the sides of the Arrhenius equation, we get log to the base E multiplied by K is equal to minus EA by RT plus log to the base E multiplied by A. Let this be equation 1. If we plot log to the base E multiplied by K versus 1 by T on a graph, we get a straight line with slope minus EA by R, and the y-intercept as log to the base E multiplied by A. From the graph, we can see that as the temperature increases, the rate constant increases exponentially, and the activation energy decreases. As a result, the rate of reaction increases. As log to the base E is equal to 2.303 log to the base 10, equation 1 can also be written as 2.303 multiplied by log K is equal to minus EA by RT plus 2.303 log A. On dividing this equation by 2.303 on both the sides, we get log K is equal to minus EA divided by 2.303 RT plus log A. Let this be equation 2. At temperature T1 and T2, equation 2 becomes log K1 is equal to minus EA divided by 2.303 RT1 plus log A. And we get log K2 is equal to minus EA divided by 2.303 RT2 plus log A. Let these equations be 2A and 2B respectively. On subtracting 2B from 2A, we get log K2 minus log K1 is equal to EA divided by 2.303 RT1 minus EA divided by 2.303 RT2, or log K2 divided by K1 is equal to EA divided by 2.303 R multiplied by 1 by T1 minus 1 by T2. Thus, the Arrhenius equation can be used to calculate the activation energy at different temperatures if the experimental values of the rate constants are known. Now let us solve a numerical problem. The rate constants of a reaction at 823 Kelvin and 898 Kelvin are 1.1 liters per mole and 6.4 liters per mole respectively. Calculate the energy of activation. The first step involves writing the given values of T1, T2, K1 and K2 respectively, and the value of R in joules per Kelvin per mole as shown. The second step involves writing the Arrhenius equation at two different temperatures as shown. The third step involves substituting all the given values in the equation. On substituting and solving, we get EA is equal to 1.4 multiplied by 10 to the power 5 joules per mole.